Hi class, we are on chapter 1 and this is pretty much 15.2. 15.1 is usually a story. So chemical kinetics, when we discuss kinetics, we're looking at the rates. So in this case, we're looking at the rates of chemical reactions and the factors that can affect it, such as temperature. The reaction rate is the speed of the chemical reaction. That is how fast the reaction goes. So how fast does it produce products, or how fast does it use reactants up? This is important because I worked in a lab, and when we would spend $50,000 of material, you want as much product as you can get. And if you have a reaction go too long, you can have it decompose or create side products. And if it's creating side products, it's not producing the product you want. And these are two factors that you want to be able to stop. And if it doesn't go long enough, then we're not producing the amount that we should be producing. Rate is how much a quantity changes over in a given period of time. So this is a ratio. So if you think about the distance over time, so this is miles per hour is a good way to look at that. That's a rate. So the rate of a chemical reaction, or the reaction rate, is defined as the change in concentration of a reactant, or a change in concentration of a product over time. It's measured as the disappearance of a reactant, that's where the negative sign comes in, over time, or the appearance of a product with the plus sign over time. And there's different units you could use depending on what you need and how fast and slow that reaction is. So M is a capital M, that means molar, and moles per liter. So in this case, there's molar per hour, millimolar per hour, or micromolar per hour for slower reactions. So reaction rates, again, they are monitored. We look at the change in concentration of either reaction or the product over time. So we're going to use the square brackets, and the square brackets mean concentration. This is the equation that we're looking at for rate, for reaction rates, and which one you're interested in looking at. So what this means is, for a generic reaction of A to B, A produces B. 1 mole of A produces 1 mole of B. This means that the rate at which the concentration of A decreases, or as the rate in which the concentration of B increases over a specific amount of time. Now, one thing I want to point out, this is the negative sign I was talking about. The negative sign has to be there because the value eventually will, the value will end up as positive. So we need that negative sign there to help make sure that this ends up positive, because it won't do that without that there. And so A is negative, but the B is positive, and we just don't write the positive. So defining the rate of chemical reaction, again, measured in terms of either the reactant or product concentration. If we look at hydrogen, just the hydrogen gas itself, we want to set it up for a reaction rate. Then you put the negative sign. The delta means change, and you're going to have two of them. One for the concentration of hydrogen, one for the concentration of time. And if you expand them out, now you see that the delta is gone, but we have 2 points, T1 and T2. If you're picking a point at T1 for the concentration, you have to take the time that goes with that, and the same thing goes for T2. So these could be thought of as final minus initial. However, you can pick any place in this reaction, so it's not necessarily have to be at the beginning or the end. It's just the initial point that you picked, and it's being subtracted from the final point that you picked, and the same for the concentrations. So if we look at a visual here, for a fast reaction, we have all reactants at time 0, but let's say this is a minute, so at 15 seconds, we have about half and half reactants, half products, and then at 30 seconds, we have mostly products, and at 45 seconds, not even a full minute, we have all products. Now, slow rate, we have time 0, we have all reactants. In 15 seconds, we have mostly reactants and 1 molecule of product. And then at 30 seconds, we have another product. We have about 2 molecules of product, but mostly reactants. And then eventually at 45 seconds, we have equal amounts of both. So here is a graph that shows what I was talking about. So we have on the x-axis, it's time, and it increases going this way. On the y-axis, it goes up, and we're increasing for molarity. So this is concentration. So as the concentration of A decreases, the concentration of B increases, and that is the rate of reaction. We can pick spots if we wanted to on here. For reaction A, such as AB, this is a 1-to-1 relationship. That means 1 mole of A is used up to produce 1 mole of B. But what happens when you have different coefficients? So in this case, the reaction for 2 moles of A produces 1 mole of B. That means that A disappears at twice the rate that B appears. when you set up a reaction rate, you have to account for that coefficient. So in this case, we have a coefficient of 2, and that has to be placed at the bottom with a time. That's adjusting for the fact that you have two different a reactant and a molecule and a product, and they're going at two different rates, so we have to adjust for that. So any coefficients go with that reactant, negative sign, and it sticks at the bottom. You put that with the bottom of the with time. So again, here's another graph. As you can see, the same thing. These graphs are actually different if you start comparing them, because the coefficients and all these, they do affect the slope of the lines. So many reactions involve more than one reactant or product. Same thing. So now we have two products for 1 mole of A. You just keep setting it up the same way. If it's a reactant, it's a negative sign. If it has a coefficient, it goes on the bottom. If it's a product, you can leave the plus sign on it. And then here is another one. Now notice there's, for every 1 mole of A produces 2 moles of C. So that's why you see a very sharp incline on C as compared to what B is. Okay, so this is a generic term again. So for coefficients, we use A and B, and those are always on the bottom. So it's pretty much everything I've just been saying, but just in generic terms of it. You have to adjust for the coefficients, and those would go on the bottom with the time, change in time. So if we look at this reaction again, we have for every mole of hydrogen is used up, we also use up 1 mole of iodine, but 2 moles of hydrogen iodine are produced from this. So the rates are going to be different from them, and you have to account for them. So again, here's just a generic for how many you have. If it's reactants, it's negative. The coefficients are on the bottom. If it's a product, it's a positive, and those reactants go on the bottom. So for a generic reaction of A producing 2 moles of B, express the reaction rate as an equation in terms of the rate of change of A and the rate of change of B, and express in words how the rates of change of A and B are related. So it's everything that we've just covered. You set up the reaction rate, but first let's look at what the words are to explain this. 1 mole of reactant of A is consumed for every 2 moles of product that are made. Therefore, the rate of disappearance of A is 1/2 the rate of appearance of B. And what that's saying is that because there is, for every 2 moles are produced, that we have to adjust for the fact that A is not being as consumed as fast as B is being produced. Okay, so the reaction rates can be measured as average rates or as instantaneous rates. For average rate, the concentration is measured at 2 times, and the change in concentration is divided by the change in time. Instantaneous rates are measured by plotting concentration versus time. So here you have to plot it out. You're going to have data points, you're going to have to plot it, and we're going to have to look at the slope and take the tangent of the slope of the tangent to determine what values we need to use. Instantaneous rates differ greatly as the overall reaction slows because we're not using as much reactant. So the instantaneous rate is in the change of a concentration at any particular one particular time. So we're looking at slopes of a curve. We have to graph in order to get this. The instantaneous rate is determined by taking the slope of a line of a tangent. So if we look at this, this is a tangent. If we are interested in any of these points that are touching or should look like they're touching, then we would take information that covers that. So we could determine what the instantaneous rate is at any point on the slope. So this one here, what you would do is they take a slope and they take the ends of the line. So in this case, this is so if we look at time, they're taking the time here and the time here and subtracting the T2 from T1 from T2. And so this is time, and here is concentration. So you're taking 2 points in that time, and you're using that to set it up, for the subtraction, and it'll give you the rate. Now, one thing I want to point out, we're also taking the same, so this is how the hydrogen iodide is the product, hydrogen gas is the reactant. So as this is being used up, this is being produced. How do I know? Because if you pick any of these points across from each other, you see that the rate is the same. So we've made the adjustments for the rate by using the coefficients. And so you can see that the rate now is matching. So chemists often determine instantaneous rates as close as possible to the start of a reaction, which is time 0. And these are called the initial rates. As rates go on, the rate of the reactions generally slows down because the concentration of reactants decreases, because we don't have as much, so it's not going to keep going fast like in the initial. And sometimes the reaction stops either because the reactant runs out, so it's gone, limited reactant, or because the system has reached equilibrium. So the rate of a chemical change, the average rate, this is again just expanding out. We pick 2 different points in the concentration, and we match that time that goes with that point for T1, and the same thing for T2. Then we subtract, and then we divide, and we will come up with a rate with the units, has 2 units to it, molars per second in this case. And the larger the time interval, the more average rate deviates from instantaneous, as it would, because it's not going as fast as it proceeds, and we're using up more and more reactants. So here again is that same slide that I just showed you. Okay, so the average rate of reaction, let's take a look at this. This is in intervals. It starts at 0, ends at 100. It's increments of 10. How do I know that? Because here's the change in time. They're all 10 seconds, but it is going. It's not at 10 seconds. It's intervals, change in time at 10 seconds. So any interval here, it has subtractive 10. Here is the concentration of hydrogen gas. Here is the change in the concentration of hydrogen gas. Here's the change in time. And here's the overall rate. Excuse me. Here's the overall rate for the change in concentration of hydrogen gas over a specified time. And then here's a graph showing the AB, which is pretty much just showing A right here, which could be very similar to what's here. This is a reactant. Okay, so use the concentration and time data for the reaction of AB to determine A, the average rate between 10 seconds and 30 seconds. I messed that up. That should say 5 seconds here. And these numbers here are not going to look. So let's just pretend this slide doesn't exist, and let's just jump right over here. The times are different. I didn't catch that until later, and I forgot to change the other slide. So the average rate between 5 seconds and 30 seconds. So you take the information you have, and here we have 5 seconds, and we have the molarity that goes with that, and then we have 30 seconds and the molarity that goes with that. And I just noticed that this is switched, and it shouldn't be. I don't know why the slides are giving me so many. As I'm going through them, this is like the 20th time I've gone through slides. I keep finding mistakes that they made. So just know that when you take T1, that's going to be always the initial, and then you're going to take T2, because these are transposed. This should be the final. This should be here, and this one should be here, because this goes with the 5 seconds. So just make a mental note that these numbers on top should be switched. And now I don't know if this is correct, but that doesn't matter. It's showing you the steps on how to do it. Okay, plot the data and draw a tangent to the curve at 10 seconds. So we have information. So let's say we plotted this out, and this is what you're going to get. You're going to get a line that's closest to what you want. Now in this case, this is close to 20 seconds. So how do we do this? Well, the slope is, remember, we have the y-axis over the x-axis. So you take 2 points. So in this case, let's look at the bottom one. It's easier to understand, which is 40 seconds minus 0. Where did that come from if you have 20 seconds? Well, the slope is at 20 seconds, but the tangent line is where the points that we're taking the information. So in this case, the initial time is 0. It's on the 0 line. And the final time, what's pretty much hitting here, the final time is at 40 seconds. So this is where the 40 seconds, it's x2 minus x1. And for y, we're looking at this way now. So we have a concentration here and a concentration here. We set them up and subtract them and take care of this. And this is giving us our instantaneous rate. This is the rate at that time of 20 seconds. So many substances absorb electromagnetic radiation, which can be measured in the lab. So colorful substances absorb visible light, and many seemingly colorless substances absorb light in the UV range. As the concentration of substances increases, then the electromagnetic radiation is absorbed, making it possible to monitor the changes in concentration in real time. What does this mean? So there's ways to monitor this. This polarimetry, this measures the change in degree of rotation of plane polarized light. So we can determine if it goes clockwise or counterclockwise, and we can use that information to measure how many, because if a reactant changes light one way and the products change in light the other, we can figure out based on this the concentrations. Spectrophotometry, this measures the amount of light at a particular wavelength absorbed by one component over a matter of time, and the component absorbs its complementary color. And then pressure is even one way to determine. The total pressure of a gas mixture is stoichiometrically related to the partial pressures of the gas. Aliquots are samples we are drawn off. So in my grad student days, I used to have to do this. We used to work with a mixed solution that we would have to take aliquots in at certain times and keep track and see what was going on. With what we used, it was UV, so it would actually change colors of the rainbow under UV light to it would show in the round bottom, which is the flask we would use. And so we would take it out and we'd use a certain light to see what the color was, and that would give us an idea of how long that reaction had to go. But we take samples out and test them at certain times. Titration from one of the components, gravimetric analysis, these are things that aliquots are used for. I don't even know what that's saying there. Gas chromatography is another way to measure concentrations and various components in a mixture. For samples that have volatile components, separates mixture by adherence to the surface. Oh, that's what that means. Okay, so here is one with the wavelength. So this is the light shines through and it detects how much light is absorbed and how much is absorbed, and you see as it absorbed, very little light gets out. So that can be detected, and you can even graph it by the absorbance. So as the absorbance increases, that means that the concentration is also increasing on here. Methods for determining concentration. So this is another way. This is reading the UV under UV, and this is a gas chromatographer. Well, it's not showing, it's sort of showing. You put it here, it gets through these columns, and then eventually it is through the detector, and it would give you a graph to be able to give you the information about that. And that's it.